Okay, we need to be able to explain why some nuclei are stable while others are unstable. And it's to do with the relative numbers of protons and neutrons and the forces involved. If we do a graph of the number of protons against the number of neutrons, for very small nuclei we find that they're equal. In other words, you would have 2 protons and 2 neutrons. You would have 6 protons and 6 neutrons. N is equal to Z line. Okay, but what you notice is that those nuclei which are actually stable tend to drift to be above the line. So what happens is that there's a larger number of neutrons than there are protons. Why? There are more neutrons than protons. That's what we need to look at. If we can look at this graph, there's lots of things it can tell you. If we're here, this point here, we have probably too many neutrons, so we have to move in this direction. So what will happen is that the neutron will turn into a proton and will emit a beta particle. And this is what is happening here. Neutron turns into proton, and we emit a beta particle. So it goes from there to there, from there to there. 1 neutron less, 1 proton more. On the other hand, on the right side of this, we tend to have alpha emitters. We tend to be moving down by 4 there. 2 protons and 2 neutrons. So there's quite a jump there. In the middle, we have the stable nuclei. Why are they stable? So if you plot the neutron number against the proton number, you get this pattern with this branch of stable nuclei in the middle. Approximately the number of protons equals the number of neutrons. Stability. We know there is a force which is repelling the protons from each other, which is the electrostatic force, which is a repulsive force. So the nuclei should explode, but there's an even stronger force, very strong force, called the nuclear force that holds the nucleons together, and it holds all nucleons together, the neutrons and the protons, and the neutrons to neutrons and protons to protons. This is the force that is there, but it's a very short-range force. The problem with the electrostatic force, is that it works over a long distance. It's got a long range. So this is another point. So the strong nuclear force has a very short range. The electric force has a longer range. So if you have the nuclear force, the strong nuclear force, these nucleons attract only the particles, only the nucleons that are very close to it, whereas the electrostatic force, this repulsion force, is not only good between neighbouring protons, but also protons that are quite far away from each other. So it works much better at a distance than the short-range force. So therefore, you need more neutrons to hold the nucleus together, because you need to provide extra neutrons, because more neutrons provide more of this the strong nuclear force. So if you have a surplus of neutrons, you're able to increase the amount of the attractive force, this strong nuclear force. So also, there's an upper limit to the size of a stable nucleus. Nuclides with Z numbers, proton numbers greater than 83 are not stable. The nature of radioactive decay is a random and spontaneous process, and it decreases exponentially with time. You need to know that the exponential decay decreases to half its value in a certain amount of time, which is called the half-life. And this half-life is independent of the original number of particles. Okay, in class we can do a simulation of radioactive decay. and this is we use it on Excel, and this is the how we would use it. Okay, you need to define the term radioactive half-life. So, from a past paper exam, the radioactive half-life is the time for the activity to halve in value, or the time for half the number of nuclei to transmute to a nuclei of another element. The decay constant is the probability of any one particle decaying per unit time. The chance of you throwing a 6 or 1 over 6, and if you throw the 6, then that die transmutes, then you could say that the decay constant is 1/6. The decay constant of a coin is half, because there's a 50% chance of it becoming a head or a tail. The relationship between T half, the half-life, and the decay constant. What happens to the half-life if you have a greater decay constant? If there's a greater chance of the nucleus decaying, it means that it will happen more often, it means you're going to have a shorter half-life. We have to be able to determine the half-life from a decay curve. So we start off at 100, and it halves, and that takes 25 years. Start off at 50, time for that to halve is from 25 to 50 years, which is 25 years. If you go from 25 to half that, which is 12.5, it's between 50 and 75 years from the start. In other words, the time taken for it to go from there to here is 25 years. Every 25 years, the number of every 25 years, the number of grams of strontium that are left is halved. So we can say that the half-life is 25 years. We have a question for you. An isotope of radium has a half-life of 4 days. A freshly prepared sample of this isotope contains N atoms. The time taken for 7N divided by 8 of the atoms of this to decay is, in other words, if 7/8 N have decayed, it means you have 1/8 N left. So after one half-life, it would be half. After 2 half-lives, it would be a quarter. After 3 half-lives, it will be an eighth. So it's 3 half-lives. We know that each half-life is 4 days, and 3 of those would be 12 days. So the answer must be C.